These are problems from Chapter 17. They're due here toward the end of February in 2021. In order to answer problem 1, you're going to need Table 1 on page 588. So that tells you the index of refraction. That lets you know the speed of light through the material. So that's 2 times 10 to the 8th meters per second. And velocity is displacement or distance over time. So 3 millimeters is 3 times 10 to the negative 3rd meters. That's the speed. I rearranged it algebraically. I get a tiny amount of time. For number 4, the wavelength in air was this. Wavelength in the solid was this. We know that the speed of light slows down proportionally to the index of refraction, and the wavelength does as well. So the index of refraction is 1.595 for this. We can figure out the speed would be reduced by a factor of 1.595 also. So 1.88 times 10 to the 8th meters per second. The frequency is constant, so that's the general wave equation. I either need to use the speed and wavelength in the material or the speed and wavelength in air to be consistent. I don't want to mix those. So I chose an air or vacuum, and that gave me that frequency. So wavelengths have a very high frequency for light that we can see. Problem 11, I'm trying to convert everything into standard units. So 600 nanometers is 6 times 10 to the negative 7th meters. That's my general diffraction formula. And basically it's saying this is a certain distance away. You have your bright spots 1.8 millimeters apart. If we reduce the wavelength from 600 to 400 nanometers, what happens to that distance apart? Well, this is going to go from 600 to 400. That would stay the same. The slits would stay the same distance apart, so that would go down also by a factor of 3 to 2. So that means that the spacing here would go down by a factor of 3 to 2. Now, trigonometry doesn't work that way for large angles, say above 10 degrees, but at small angles, this distance over this distance, which is a tangent of an angle, is very similar to the sine of an angle, which is this distance over the hypotenuse. So that would give us 1.2 millimeters apart. For P17, I need to find that distance in between them. So I've got 1,000 slits per centimeter. That's 100,000 slits per meter. So 1 over that number would tell me the distance between the slits. That's 1 times 10 to the negative 5th meters. I'm given the wavelength. So I'm going to go back and figure out my d sine theta equals m lambda. So for angle 1, or the first spot, 3.15 degrees. For the second spot, about 6.3 degrees, putting m equals 2 in there. For 25 and 27, these are thin film interference problems. And my Ed puzzle was on that, but also for cohort B at least, we got a chance to talk about some of that in class. So if you're having trouble with this, hopefully we can go over these in class. So if you recall, when light hits and reflects off of a substance that's got a greater optical density than the substance it's coming from, and this would be air up here, it undergoes a phase shift, or I call it a flip, of 180 degrees, or half a wavelength. So this ray of light is coming in and reflecting off the top and bottom surface. Both of those flip because the top one reflects off of oil, which is more dense than the air. The bottom one reflects off of water, which is more dense than the oil. So that means if the thickness of this was 0, those would be in phase and cause constructive interference. But it can't be 0. So the path down, the path up, or two thicknesses are the path length difference. That's this and this. So that 2 thickness needs to equal 1 wavelength, 1 full wavelength, to keep these waves in phase, since they already would be in phase if the thickness was 0. So that means the thickness would be half a wavelength. Now you might think that that's 250 nanometers, since it told you the wavelength in air, but if you remember, the wavelength decreases when we go into something that's more optically dense. So I'm going to take the wavelength in air and divide it by 1.25. That gets me my new wavelength in oil. Half of that is 200 nanometers. For 27, same sort of thing. It's a longer wavelength, so that's 700 nanometers in air. That's red light, so I did it in pink. Reflecting off silicon dioxide and then off the solar cell. So this is used to coat the solar cell to cause reduced glare. So it's actually kind of cool. It's trying to cause destructive interference. And I wasn't aware of that before. So that means that both of these, again, will flip because they reflect off a more optically dense substance. But now we want there to be destructive interference. So this path length difference, which again is twice the thickness because the light's going down and then back up, that has to equal half a wavelength. So that means our thickness would be a quarter of a wavelength. Well, a quarter of 700 is around 175, but if you remember, our wavelength has an index of refraction 1.45, so to find our wavelength in that new silicon dioxide material, silicon, not silicone, I guess, we divide that by 1.45, that gets me 483 nanometers. A quarter of that is around 121. So still a quarter wavelength. For 48, we're told that the wavelength of light, again, I'm immediately converting it to meters. I'm told that this is 6.6 centimeters after it travels between bright spots. After it travels a distance to the screen of 2.5 meters. So again, I'm converting everything to meters here. Going to get that angle, which is tiny, by using inverse tangent. And that's 0.1375 degrees. So now I go back and use my general diffraction formula. And again, the sine of this angle is very close to the tangent of the angle. So rearrange that to solve for d, which is the distance between those two slits. And I get a very small number here. The last one, number 57, gives me how many slits there are per millimeter, and I need to figure out the distance in between those slits. So I immediately convert that to slits per meter, and then I take the reciprocal of it to get that distance, which is 2 times 10 to the negative 6 meters. So I look at this equation, and it's asking me this wavelength. It gives me two different angles. So I get the left side of the equation, and I get these two numbers. The problem is I don't know the m values, and I don't know the wavelength. But if I look at this ratio, 1.91 to 1.43, that's a 3 to 4 ratio. So that tells me that m here would be 3, and m here would be 4. Because we generally deal with small numbers such 1, 2, 3, and 4, you probably wouldn't be above 5. At any rate, so when I do that, and I plug 3 in for this equation up here, or 4 in for the m down here, either way I get that the wavelength is 477 nanometers, or 4.77 times 10 to the negative 7th meters. And hopefully those help out. Thanks.